Okay, so last time we went through the basics of oriented projective geometry and talked a bit about duality for polytopes. So this is basically like how you can convert between a vertex polytope and an H-polytope. That would basically be two different polytopes represented by either the set of points or interpreting the points as a set of half spaces. And so today we're going to start looking at some questions or things that we can compute on polytopes in oriented projective geometry or other variations of that. And so, you know, in this lecture and the next lecture, we're going to be looking at basically different types of predicates or constructions involving polytopes and how we would calculate these things. And probably the simplest possible question one could think about asking of a polytope is whether or not a given point is contained in that polytope. So here, and this is basically going to be the first thing that we're going to talk about in this lecture. So we'll say, is a point x contained in a polytope? Right? So this question doesn't look too bad, right? And if our polytope happened to be an H-polytope, then this would actually be pretty easy. So there's sort of two situations. The first case is one, P is an H-polytope. That is, P is going to be equal to this intersection of, let's call them A's for now, right? AI. Which, if we write it in sort of a set theoretic notation, is that this is the set of all points y, we'll say in projective space, where some big matrix A transpose times y is less than or equal to 0. Where by convention, for the rest of today, we're going to be calling this matrix A a matrix whose columns are just these AIs. So we'll say A0, you know, all the way up to AN minus 1, right? And two bits of notation that we're going to keep with us here is we're going to say D equals dimension, and then N equals number of points slash half spaces, depending on the context. All right. So in this case, if P is an H-polytope, and we want to check if a point X is inside P, then this is really easy, right? We just have to plug it into this formula here and then check that it's less than or equal to 0. So it's like really straightforward. So in this case, we'll say X is contained in P if and only if A transpose X is less than or equal to 0. Right? How expensive is this? Well, we have basically this matrix here, which is going to have n items in it, and then the dimension of the space is D. So this is like, you know, trivial order n D complexity. I mean, it's really simple, right? I mean, you can ask a little bit about how many bits it would be necessary to do this, but don't worry about that now. So that's the simple case, right? So if we want to test if a point is in an H-polytope, no big deal. Now, what happens if P is a V-polytope? And this is a much harder question, it turns out, and the one which we're going to be looking at today in detail. So the second case, P is a V-polytope. And here we have to do some work. So if P is a V-polytope, then that means that P is going to be the cone of this set of all these AIs, right? So it's basically all these conical combinations of each AI. And that means that this is the set of all y such that y is equal to a times, or such that there exists some parameter c, right? Whoops. In Rn, where AC equals y, and each of these c's are greater than 0. All right, so this is the harder problem. And so we'll say that x is in P in this case if and only if there exists some c such that AC equals x and these c's are greater than or equal to 0. And this is a little harder to solve because we have this existential quantifier here, right? So we're saying that there has to exist for some c. We don't know what it is. We got to solve for it somehow. So the question is, where do we get this c, and how do we find, this parameter here, right? So there's a lot of different ways to approach this problem, but I'll start off with one terrible answer, right? Which is we could use Fourier-Motzkin elimination, obviously, right? It wouldn't really be a very practical way to do it, but it would work, right? So at least we know that there will be a solution if it exists, or we can rule it out. So there's a simple kind of brutal algorithm, but obviously we could do a lot better. In the case where our dimension was 2, right? So we'll say if d equals 2, we could use convex hull, right, from last time to basically convert this thing into an H-polytope. Use convex hull, convert to H. So basically convert this whole thing into an equivalent H-polytope representation. And this would take order and log n, and then testing it would be plus an order n, which we can neglect. So that's no big deal, right? We haven't seen it, but it turns out same is possible for D3. And it turns out in higher dimensions, this doesn't work so well. And the reason that it doesn't work, which we'll come to again later, is that the convex hull of a set of vertices in general position is generally much larger than n. So as we go to d equals 4 and higher, we're going to end up with order n squared or order n cubed or some massive amount of vertices. It just so happens that in 2 and 3D, we end up with the same number of facets, roughly, as the number of vertices that we started with, which is a fortuitous situation in low dimensions, but not something that we can count on. So this becomes slow in d greater than 3, right? The other kind of annoying thing here, too, is we have this log factor, and it would, of course, be nice if we could get rid of that and do this in linear time somehow, right? So, okay, so this is sort of the simple solution to this problem, but we're not going to worry too much about converting it into, an H-polytope by taking a convex hull today. Instead, we're going to look at some alternate solutions. So I'm going to erase this now. So we're going to start with a couple of simple brute force algorithms. And initially, these will be a little bit worse than what we could do with convex hull, but we'll quickly catch up and surpass it. And by the end of the day, we'll even be doing better in the 2D case, hopefully, if we have enough time. So we'll add the constraint V-polytope, right, because it's important. So, OK. So is a point x in P if P is a V-polytope. And again, we're going to assume now that P is going to be equal to the cone of these AIs. All right. So let's draw a picture here. Call this guy A0, A1, etc. Right? And we'll suppose that we have some point here. Let's call this one x. Right? And so we want to basically check if this point x happens to be contained in the convex hull of all of these other points. So one simple observation is that if a point x is contained in the convex hull of these points, then there has to be some triangle or simplex within the set that contains the point. So if x was contained in there, then there is some triangle that contains x. So we'll say, here's the observation. X and P implies that there exists some AI, AJ, etc., AK, where X is in, there will be D plus one of these guys, of, let's call it delta, which is going to be this thing, right? So delta for simplex. All right. D plus 1, right? So in 2D, there's going to be 3 points. In 3D, there will be 4 points. In ND, there will be 5 points. And then the weights, right, if we wanted to solve for the weights C that we're going to put on them. So we'll basically say then x is going to be equal to, actually maybe I better use different names for these things. I'm going to call them T. Sorry, guys, for changing notation like that, but it has to be done. So we'll say it's C0, T0 plus C1, T1, etc. For this triangle containing these guys, we'll say it's T0, T1, T2. Something like that, right? So these coefficients, we've seen this sort of story before, right? Anyone know what's going on here, right? Or what these coefficients C would happen to be in this triangle? I'll draw a picture. Maybe this will help. Come on. What are these things? So remember, we learned that the coefficient on T0 is going to be proportional to the area of this triangle divided by the area of the whole triangle, right? This is like maybe a little bit early. Anyone remember? OK, they're barycentric coordinates, right? So this would basically just be the barycentric coordinate representation of x. So I'd say these CIs of x in delta, right? So if we can just find any simplex, right, that contains the point x, right, then we can solve for these barycentric coordinates, and this will give us a set of weights that we can use to represent this point as a convex or conical combination of points in our polytope here. All right, so that's the sort of simple story, right, for how we could do this. So this immediately suggests a very simple algorithm, not necessarily an efficient one, that we could use to test if a point x is contained inside this cone. And the way by which we would do this is just enumerate all possible simplices, right? So all d plus 1 tuples of points inside this set. And then all we have to do is for each d plus 1 tuple, we solve a linear system to get these coefficients. And once we have them, then we're done, right? So this is the brute force algorithm. So brute force for each d plus 1 tuple of points in A, compute barycentric coordinates, right? And if it turns out that x is not contained in any of them, then we're done. So we'll say if no triangle contains x, then done. All right, so that's like the really kind of naive algorithm. And the time for this is going to be order n to the d plus 1. All right, so that's a starting point. But we can modify this a little bit and get it to run somewhat faster in higher dimensions too. And the observation behind this is that if we've already computed one of these simplices, then in some sense we know where this point is going to be relative to the rest of the points in the triangle. Because if one of these barycentric coordinates is less than 0, then that means that on that face of that simplex, the point has to be over there. So we can just take the vertex opposite that face and move it to some other vertex. So here, I'm going to sort of walk through a kind of high-level version of this algorithm, give you a very sort of intuitive description of what's going on. So the idea is we start off by picking some random simplex inside the set. So maybe we start out here. And then we calculate these triangles, right, and the areas of them. And we'll see that maybe this edge here, right, x is behind that one. So then what we can do is we can loop over all the points again and replace this vertex of the triangle with a new vertex, right? Maybe this one here. So I'll use another color. And we'll form a second simplex right here. Right? Then we repeat again. And then maybe we end up with a third simplex like this. And then we repeat again, loop over all the vertices, and we finally end up with this simplex here that contains x, and then we'd be done. Right? So this is sort of the simple gradient descent type algorithm, which is we imagine that we start from some initial guess, and then we just keep walking until we finally find a simplex that contains the point that we're looking for. So this is our second algorithm. I'm going to write this out here. We'll call this a simplex algorithm because we're looking at simplices. So initially, it said delta equal to random d plus 1 tuple. Doesn't even matter, right? Then we'll say, OK, well, true. Let's compute alpha equal barycentric chords of x and delta. Just basically just do a linear solve, right? So we'll say if some parameter alpha sub I is less than 0, right? So we have some component of these alpha i's which is less than 0. Replace the ith value of delta with some point ai, where orient of this delta, where we basically replace delta I with ai, kind of creating some weird notation there, but you get the idea. We're just going to go through delta, take that ith entry and swap the ai in it. So we want to basically find some point which is going to be to the opposite side of the simplex as this thing. So it should be less than 0.
Do you have to iterate through the points in order?
Yeah, exactly. Yeah. So you have to do a scan over all points. So this is an order n operation to do this, right? And we should also say if no point possible, or we'll also say if no point is found, return x not in P. Otherwise, after this thing, we'll say otherwise. Return x in P, right? And actually, the solution for the barycentric coordinates will just be these weights alpha applied to the simplex delta. So the running time for this algorithm is a little bit hard to understand. First of all, I wrote it in a kind of sketchy way, right? Because you have to be a little bit more careful with how you do this replace step here. But you're right, though. Like, it would take order n operations in order to do this. So the question is really, how many times is this outer loop going to get run, times the number of times we have to do this inner loop, which is going to be a full replacement. And then we have some extra stuff here where we have to solve for the barycentric coordinates, but this is only like a d cubed type operation, because it's basically solve a matrix. So this is actually an open question, really, about how long this would really take. In practice, it's usually pretty fast, right? So typically it ends up being polynomial time in most reasonable cases. But there are instances and variations of this where it can take an exponential amount of time to converge. It's also somewhat sensitive to the way in which we select this replacement point AI, because I only required that it was less than 0. But for example, suppose if instead of replacing this vertex here with this vertex, I decided to replace this vertex with this vertex, then it would have converged maybe like a couple of steps faster, perhaps. Right? So there is some weirdness in how we select these vertices. But I'm going to claim, and you're just going to have to take this on faith, that in practice, for high dimensions, this works out to be pretty damn fast. Right? Usually no worse than, say, quadratic time, which is pretty good if you're going to be in greater than 3D. Right? Usually much better than that. Right? But again, it depends, how many times you're going to or how you're going to find these replacement vertices and how these steps are going to be taken. So this is sort of the simple way to sort of walk through this set of points until we find some replacement vertex and do that. Now, in the worst case, though, how long would this be? Right? So the worst case complexity is we could still possibly end up iterating over all of these different possible d+1 tuples of vertices. And so it might not be any faster than the brute force algorithm in the worst case. Right? But in higher dimensions, this is probably your go-to algorithm if you need to go test if a point happens to be contained inside a convex hull of points. All right? So that's the general purpose algorithm. But we don't care necessarily about the general case in this class. We're mostly interested in low dimensions. Right? So we want to look at what happens in 2, 3, 4, and 5D. Right? Maybe not so much about like 100D. So in these lower dimensional cases, we can actually do way, way, way better than this. But to do this, we're going to have to change our perspective on the problem a little bit. And we will do this using duality. So let's start out, again, with this problem for V-polytopes and consider the dual version of this problem that we're trying to solve up here. So this is a theorem. We'll say that a point x is contained in P if and only if the dual of the polytope is contained inside the dual half space represented by that point. Right? So what does this mean, right? And how do we actually interpret this? Well, I could just wave my hands and say duality, right? But that's not necessarily the most convincing proof. So let's go through this and work out why this is true in more detail, right? So to start out, right, we're going to assume, of course, that P is a V-polytope in this case, right? So we'll be focusing on that particular example, though it shouldn't matter, right, because it's just a polytope. But this will also be illustrative for the algorithms that we're going to be caring about. So what does this mean, right? X is in P if this happens to be a V-polytope. Let me go pull up my notes here. Right. This means X is in P if and only if there exists some parameter C such that A times C equals X, and these C's are greater than or equal to 0, right? So that's what this means for V-polytopes. So I'll say V-polytope version. Similarly, we have this thing here, right? So what's going on? Well, we're going to say P star is contained in X star if and only if, for all y such that a t y, so basically this dual of p, right, the transpose of a is less than or equal to 0, x transpose y is less than or equal to 0. Right, so this is basically the H-polytope picture, or the dual version of this left-hand expression. And so at this point, we're almost done, though it might not be clear at the moment. But we'll kind of prove the forward direction first, and the reverse direction ends up being kind of identical. So here's how this works. So we're going to basically build like a chain of reasoning. So we'll say x is in P implies that there exists some C such that AC equals x, and each component of C is greater than or equal to 0, right? Now, what does this imply? If we take this thing here and multiply it by A transpose, right, on both sides, right? Or if we take the transpose of this whole thing and then we multiply it by any parameter y, that's going to be greater, or that's going to be greater than or equal to 0. Did I do this right? Hold on, let me go make sure I put this correct. Right. I think I maybe flipped a direction. Right. Okay. Yeah. No, this is still good. This is still good. So this means that if I take x transpose times y, right, this better be equal to C transpose A transpose y, right? Because I'm just taking the transpose of this thing here, sticking it in by y, right? But now I know that if A transpose y is less than or equal to 0, that is, it's contained in the dual polytope, then I know that this sub-expression here for every term is less than 0. These C's are greater than 0, right? So this whole thing here is basically a positive value, our C, times a negative value, our Y. This is going to be less than or equal to 0, which means that this point here, y, is contained inside the dual half space x star, right? And so this implies P star is contained in x star. So does everyone follow that? So that's the first chain of reasoning, right? Now let's see here. So how do we do the other direction? Right. So, okay, let's go the opposite way, right? It's sort of the same type of thing. So now we'll start out from this other version. So we'll say, okay, so suppose P is contained in x star. This implies that for all y such that we have A transpose y less than or equal to 0, x transpose y is also less than or equal to 0, which now means that because the A transpose y is less than or equal to 0, say then what's the right way to do this? Right. So here's what we're going to do. We're going to basically guess that C is equal to negative A transpose y Right. And now if I take that and plug it in, c is going to be greater than or equal to 0. And when I multiply this through here, I will get a transpose y equals x. And this will all be less than or equal to 0 because of the, I don't know. Don't want to waste too much time on this. Do this right. Should get C transpose A transpose. Oh. Shoot. My notes are really messy right here. I'll post a better solution for the opposite version, but it's basically just symmetric to the first case, though. But I can't read what I wrote here in my handwriting, unfortunately. So we're just going to have to punt on this a little bit. But suffice to say it works. Did everyone follow the first direction at least? Right? Yes or no? All right, I'm going to erase the dual version. I'm sorry if this confused everyone. I didn't prepare that well enough. Right. OK, but this is the idea, right? So we all see like what's going on in the forward direction. The dual version is just the reverse. I just made a typo somewhere. I'm not going to try to debug it right now. Right. But this is the idea, right? So if you have this x is contained in P, we have this AC equals x, substitute that value into here, into here, right? Into this equation. Then we get this A transpose y is less than or equal to 0, which then gives us the final result, right? So that's that direction. The other direction is pretty much the same, but yeah, you can work it out for yourself. It's not a big deal, actually. I'm just not going to try doing it right now. OK. All right, well, that was a lot of work to prove something that we could have said in a much smaller amount of time, right? But it should hopefully emphasize that this duality thing is consistent and it does work, right? So it's always nice to have multiple ways to check it. But more than that, because of this duality, it means that if we want to check if this point x is contained inside P, then that means that we can also check this other formula here. So that means that if we can basically check that the dual polytope P star is contained in the dual plane X star, then we can basically answer this by some other means. And we're going to now look at this dual problem here and try to solve this instead of trying to solve the problem here, right? And this will give us a different algorithm with different techniques. So here's the idea, right? The result of this theorem, the moral is these two problems are really just equivalent. So a solution here implies that this thing is good. So, all right, what we want to be able to solve now is we want to say that for all y, right, such that A transpose y is less than or equal to 0, we're going to require that X transpose y is also less than or equal to 0. So that's what we're saying, is that for all of these y's, that should be the case. Said another way, right? So another variation of this problem is we'll consider this. So suppose we want to solve this problem of minimize all y in RD, whatever, such that you have this quantity x transpose y. Right? So we want to minimize this function such that A transpose y is less than or equal to 0. All right? And here's the conclusion. We'll say that if x transpose y is greater than 0, then x is not in P. That's the moral, right? So this is sort of the bottom line, right? So if we can solve this problem for y, and if at the end of the day, the smallest possible value that we could pick here for y ended up giving us something that was greater than 0, then we definitely know that x is not contained in the polytope. That's the conclusion, right? So this is the problem we want to solve, this thing. It's basically minimize some linear function subject to a set of linear inequalities. And this type of problem shows up all over the place in a variety of different settings, and it's what's known as a linear program. In fact, the other stuff that we've been doing so far today are other variations of linear programming. So that's what this thing is right here. And there are a number of different methods for solving these things, which are known. In high dimensions, which is sort of the case that most people are concerned about in convex optimization, variations of that simplex algorithm, which we saw earlier today, are what are used commonly to solve these problems. So we'll say that there's sort of two general classes, or maybe three, depending on how we choose to count it, of linear programs. So there's sort of three situations. So the first one is that number of constraints and dimension high. This basically implies use simplex method, or there are other techniques, right? So these are sort of like not really computational geometry problems. These would probably be more in the realm of the things that you'd see in convex optimization. So this is in the situation where you have, a huge number of constraints and a huge number of variables in your linear program that you're trying to solve. Right? And so this case, you're basically stuck doing something like that simplex type method. It's going to probably converge in some, super linear time, right? Maybe it becomes pretty messy. Like the best algorithms converge in roughly, cubic time in the number of constraints, or somewhere it's like n to the 3.5 is sort of the best known time complexity. The other situation is where we have many constraints, few variables. So this is sort of the situation that we have here, right, when we're looking at the point in polygon type of problem. So here, the dimension of this space D is typically going to be very small, but maybe the number of points that we're going to be looking at could be enormous. So here, n is basically like way, way, way larger than D. And we're going to look at some algorithms for doing that today, right? And then the final case is small, we'll say a few constraints. Small or big dimension. So this is basically the D greater than N. And this is basically the dual of this situation. So if we wanted to convert from this type of scenario where we have like maybe a handful of constraints, for example, in this case here, right? And then like some enormous number of variables, then we can just take a dual and then convert it into the opposite problem, and then we're done, all right? So these are basically the three different cases. We're going to focus on number 2, because if we can do that, then by duality, we can also get the third one, right? So it's not going to be a big deal. And so this is the problem that we're going to be looking at today, how to solve things of this form, minimize linear function subject to linear inequalities. All right? And we'll probably spend some more time talking about it tomorrow, maybe in some more abstract generality. Right? So that's the basic issue. So, right, go clear up space on the whiteboard. All right, so here is our new problem, which is equivalent to the problem we were trying to solve before, which is basically minimize xty for y in Rd such that A transpose y is less than or equal to 0. All right, so this is the fundamental problem. And it's a linear program. All right. So, okay, again, we'll start out with kind of a variation on brute force again, but we'll see that we can very quickly modify it into something a little bit better. So, okay. So here is sort of a picture of what's going on here, right? So if we think in terms of a number of half spaces here, we have some region P star, which is equal to the intersection of all of these HIs. So this could be like H0, H1, H2, etc. They're all oriented in some way, right? Then we have this region, which is cut out. And similarly, we have this vector field here, which is sort of the x star direction. And this is basically ranking all of the points in this polytope. And there's going to be some solution here, which is the farthest along the negative x star direction. So this is actually the negative x star point where all of these are going. And then this will be y. So that's the idea. So we have some sort of vector field which is pushing all of the points towards some sink or some extreme vertex of this polytope. And so this already kind of tells us a little bit about the solution here, right? Which is that intuitively we're going to expect that the value of y, which optimizes this problem, is going to be some vertex of the polytope cut out by all of these a's, right? So that's the mental picture of what's going on. And so if it is a vertex, then one sort of brutal algorithm is we could just loop over all of the vertices. And so for every d tuple of vertices, just intersect them all together and then check the vertex if it's sort of optimal or not. So just exhaustively check all of them. The one slight flaw with that, though, is that we also have to make sure that the vertex which we select is actually contained inside the polytope. So once we get a vertex, we need to make sure that it's not something like, if you imagine if I carried out these 2 points over here, this would be something that would look like a d-tuple of planes, right? But it's not actually contained inside the intersection of all of them because it violates this plane. So what you have to do is say, okay, loop over all d-tuples of planes, compute that vertex for that d-tuple, and then loop over the remaining set of planes again, and then check that it's contained inside each of them. So that's sort of the brute force algorithm. So one way we could try to maybe make this a little more systematic is we could try to enumerate these planes recursively. So here is a very simple algorithm for enumerating all of these vertices or of the polytope. All right, so we'll say this is our. All right, and so here is going to be our input. So we're going to take this matrix A here, which will basically be the points, right? We'll have our vector x that we're trying to optimize. And then we're going to have this other parameter b. And what b is going to be is the set of planes that we have looped over so far. So imagine that we're going to keep projecting onto another plane, right? So the concept that you can sort of keep in mind is that we're going to do this in sort of an incremental order. So we'll start off with like some arbitrary ordering of these planes, right, each AI, and then we're going to add them one at a time. And then each time we add a plane, we're going to check if our current solution is contained in that plane. Otherwise, we can just keep going. Or if the solution is violated by that particular plane, then we're going to project onto the new plane and then keep going, right? So here's kind of a picture. So imagine that we start out with this plane. Maybe your vertex x is like way over here. You stick another plane in. Then as we insert it, x goes there. Then maybe we insert another plane. Perhaps this one is oriented this way, so x is still good. But then maybe we insert a plane like this, and then we have to update. So maybe x moves to over here or something like that. So that's kind of the picture, is that we're going to be adding these planes one at a time. Right. So here's the idea. So we're going to first make a local copy of S, which we're going to just, or of B, which we'll call S, and we'll just store it off to the side. And then we'll loop over all of the half spaces in A. So we'll say for I equals 1, 2, the length of A. So this is basically just, for each of the columns in the matrix A, right? So we're just going to swap, loop over all columns. All right. And then, we're going to need the subroutine. I'll explain this now. So if solve B x is not equal to solve B concatenated with the ith column of A, x. Then we're going to update our solution so far. We're going to basically resolve on a lower dimensional space. So we'll call linprog on A I plus 1 to infinity. So basically take the rest of the array A and then recursively call the parameter x, then B concatenated with I, and then when we're all done, we'll just return S. So what does this solve function do, right? Let me back up. So here's one sort of simple observation, right? So we'll say solve exactly solves problem where number of constraints is less than or equal to d plus 1. Because if we have d plus 1 or fewer constraints, then this problem basically becomes compute the meat of a collection of lines or planes, and then check that the vertex is contained in or without them, right? And if this system of equations doesn't have a solution because maybe it's overdetermined, then we'll basically return not a number or no solution exists or something like that, right? So that's the basic operation of solve, right? And I can say more explicitly what happens if we have fewer than n planes, right? So if we have fewer than d plus 1 planes, so this thing is unconstrained, then what we'll do is just project our vector x, which is the direction that we're moving, onto the subspace formed by the meat of all those planes. So in more precise terms, so I'll write out what the solve subroutine does. So we'll say solve with some set b and x. All right. First say remove all b pointing away from x. So that is, to kind of draw a picture of this here. Imagine if I have a line which is pointing up and my vector x is pointing in this direction, then I could throw this constraint away, right? So the first step is you throw out all of these useless constraints which aren't even pointing in the right direction, right? So we'll just construct sort of a minimal set of constraints from this b. Then we do a linear solve of basically by equals x. It's probably b transpose equals x, and then we can just return the solution y. So we can just do sort of a return y, which is basically the same thing as just projecting onto the subspace determined by b when you compute this solution. So that's the the sort of like numerical part of this, right? Which is not too bad. I mean, we've already kind of seen how to do this in various forms through the class, so that's not an issue. So, okay. So I claim that eventually this algorithm will terminate after at least d+1 levels of recursion. And the simple reason is that eventually we're going to get down to this point where solve will basically be stabilized at the solution vector, which will consist of d+1 different points. And so adding any additional constraint is not going to change our minimal solution for this problem. And then it'll be done, right? So how long could this take? Well, in the worst case, it might actually be n to the d+1 again, right? And the way to sort of imagine this is that if you have, say, like a bunch of planes like this, and maybe like your solution is like right here. So you start off with something like this, and then you just have to keep recursing down into it over and over again. But maybe you start down here, so then you get like one of these vertices, and you keep going. So you'd have to maybe iterate a long time. So one way to kind of avoid these pathological situations would be to shuffle the planes around so that you iterate over them in some arbitrary order, so you wouldn't hit one of these weird pathological situations. And in fact, that actually works, right? So does anyone here know how to shuffle an array or like shuffle a deck of cards, right? So there's kind of a trick to this, right? It's like a little weird algorithm. It's called the Fisher-Yates shuffle. And that's the idea, is that we're going to basically take this set A, and then we're going to shuffle it as we do this loop, right? And I claim that the shuffling will actually make this algorithm go much faster. But first I should say how you shuffle, right? So the way you shuffle an array, A, is that you just loop over all the elements. So you say for I equal 1 to length of A. You can just swap the element AI, the element AI plus some random number mod n minus I. So this is the idea, right, is that you basically take the element at the position I, and then of the remaining elements in the array, you just swap them back and forth, right? So each element at the position I could have been any of the elements of the array just selected uniformly, right? So this will generate a uniform shuffle of the array. And so if we want to do this shuffle over here, all we have to do is just take this line from this chunk of code and move it right to this point in the loop, and then we can just shuffle A as we're walking over it. So the simple way to avoid the bad case is that we're just going to, in here, insert a swap, right? So we'll swap AI with AI plus rand mod n minus I. All right. So that's the simple trick that we're going to use. And then this really easy algorithm, I claim, actually runs in expected linear time. So it's actually faster than the convex Hall algorithm for calculating the solution to this linear program. So how do we figure that? Well, we're going to use a kind of weird technique which is called backwards analysis. Right? So the idea is that we're going to start from the solution of the problem and then work back to it. Right? But to do this, we're going to first need to formulate a recurrence for calculating the time complexity. So here's sort of the recurrence. We're going to write it as a function of n and d, which is the number of constraints and then the dimension of the space. So we have this function t and d. And then there are basically three cases here. So first of all, the easiest case is if d happens to be equal to 1, in which case this algorithm is just going to go through one quick loop, right, and will basically be finished, right? So in the case where d is 1, we're just going to scan through all of the constraints, and this is basically like pick the longest, the farthest point along a particular axis, right? So it's basically an order n operation. So this will take order n time if d is equal to 1. Similarly, if n is less than or equal to d, this is just solve a linear system, because it's just going to be one call to solve, and then we're also done. Right? So that's similarly pretty simple. So it'll be an order d cubed, which is basically the time complexity of doing one solve, if n is less than or equal to d. But then the hard case is what happens when n is relatively large. And in that case, there's one of two sort of things that can happen, right, at each iteration, right? So if we look at what's going to happen here, we start out with this function call. We go through this loop, right? And then each time we go through the loop, we hit this point in the function. And the real question is, will we have to do another level of recursion or not, right? So the general complexity of this whole function, right, is if we think of it, this tnd is counting, from this loop invariant, right? It will basically be the cost of tn minus 1 d plus, well, the cost of doing one call to solve, but that's trivial. It's like order d cubed. Or you can make it smaller. You can actually do it in order d time, amortizing properly, but it's tiny. It doesn't matter. Plus the probability, which we're going to just call p for now, of having to go through this inner loop mess, right? And if we do that, we will basically charge the cost of all of the previous iterations of the loop here. So we're going to basically pay an order n plus the additional cost of doing this d minus 1 recursion. So it's going to be n d minus 1. All right, so if we have to go like another dimension down, all right, that's the cost over there. So the question then is, when will we ever have to go this level deeper? And that is where this backwards analysis idea comes into play. And so the way that we think about this is that if we imagine that we already had a solution here, right? So suppose that we've already run this thing through to completion, and suppose we knew exactly what the solution planes were going to be, which are these d planes, right, that represent like the extreme vertex. Then we'll see that we'll only ever have to actually recurse here if at some level in that recursion we actually hit one of those d planes, right, that were left in our final solution. And so the odds of basically randomly drawing one of those d planes out of this whole loop, because we shuffled them, is d over m. There's only d of these guys left in the bag, and so we're going to be shuffling them so that we're going to be drawing one of these planes at random. If we draw one of those d planes, then we're going to have to hit this other layer of recursion. So this parameter p here is equal to d over m. So if you plug this in, you get this kind of nasty-looking recurrence. But it turns out to be not so nasty, right, because you can actually expand it and solve it. So, yeah?
What exactly is m? Sorry.
Oh, n, right, n. Sorry, right, d over n. It's because there's n different constraints left, right? Only d of them can possibly trigger this recursion if you were to walk it all the way out to its conclusion. So there's a probability of d over n that we're going to hit one of these constraints that's going to trigger this cascade of failures, walking all the way down. So that's the situation there. So the complexity of this algorithm, if we consider this probability to be okay, right? This is only an expectation, of course, right? It's not like a with high probability type of thing or whatever, right? You could still have runs of this algorithm that could be much worse, right? But the probability here is that when you run this thing, it's going to basically do this regular tn minus 1 d work, so this will basically terminate in like order n time, but then plus this extra work here where you have this d over n factor where you have an order n there, and then a d times the residue of that whole mess, right? So if you iterate on d, right, you imagine that we basically start from d1, so we have an order n here. Then at the next level, we're going to basically end up multiplying by a factor of d when we walk all the way through it. So that'll basically be like, say, 2, right? Then we walk up to like the next level, and it's going to be like a factor of 2 times 3, so 6, right? And then go up another level, it'll be 4 times 6, so 24. So the final complexity of this recurrence, not giving you a very formal definition, but you can work it out, will be d factorial times n, which is pretty horrendous as a function of d, but as a function of n, it's linear, right? So this algorithm for linear programming ends up being pretty damn fast if our dimension is very small. And it can actually be better than order n log n if n is suitably large. So this is our first algorithm for linear programming. We'll probably go through some other ones tomorrow, but I think with the rest of this class here, in the last 15 minutes, I'm going to go through a couple of different applications of linear programming so that you guys can get some idea of other ways that you can use this technique, which is very powerful as a means for solving problems involving polytopes. So just to name a few different ways that we can do this. And by the way, this algorithm which I just gave you here is called Seidel's algorithm. It's a standard technique for doing low-dimensional linear programming. And you can follow up with all of this stuff in deBurg, right? So in your textbook, there should be additional information that you can supplement this lecture with. Right. So I'm now just going to go through a variety of linear programming or simple variations on linear programming that don't substantially change the way this algorithm works in any real detail, right? But it's basically the same sort of story. So these are just sort of applications of linear programming. There's a huge list of things that can be reduced to linear programming. So the first thing we've seen so far is we've seen point membership, which is test if a point is in a polytope. Similarly, the dual of that is half-space containment. It turns out that intersection, so collision tests between polytopes, can be calculated with linear programming, so intersection tests. And a variation of this, which is called quadratic programming and doesn't substantially complicate any of this, can be constructed to give you distance queries. So you can compute the distance between any two convex sets and also the closest pair of points. So closest. This is very useful in physics simulation, where you might have like a bunch of rigid bodies, and then you want to keep track of the points between them, so that you can detect where they are. Minimal enclosing ball, right, is another common problem. So this would be you have some set of points, right, or some polytope, and you want to find the tiniest disk or sphere that contains all of those points. And that problem can be, again, formulated as linear programming and solved in linear time. Tangent planes and tangent lines. So tangent line calculations. Ray intersection. So this would be useful in computer graphics. So you have a polytope, you want to render it on a screen, so you have to go do these ray intersection queries, right? Which are basically cast ray against a polytope, check where it hits. Point location on the boundary. So we haven't talked much about this, but linear programming, as we've seen it here, is sort of the example where you're not doing any pre-processing. You're just, you come in cold off the street, right? And someone says, here's a bunch of points, find one of these properties of that set of points. And in that case, you would basically be stuck having to still scan through all of the variables in the problem in order to produce a solution. But there's sort of an offline or one where you're allowed to do some pre-processing, right? So some variation of this problem where you build a data structure first, and then you want to answer your linear query, your linear programming problems very efficiently. And this problem is called point location, and we're going to spend some time talking about that. This turns out to be very important in GIS applications. So you can imagine if you think of the Earth or like some ball or a sphere, right, as being some kind of polytope, then you'd like to locate the face of that polytope, for example, that a given point happens to be contained in. Or if you flatten that out onto a sheet, right, so you have a bunch of regions in a map, then that same problem can be thought of as a kind of offline variation of linear programming, where you're allowed to pre-process this map to speed up your point queries very quickly. Some other stuff we can do related to the minimal enclosing ball, there's the diameter of the polytope can be calculated from a linear program, and same with the width. These in 2D correspond to the length of the longest and smallest axis that you can draw through the center of the polytope. And there are, of course, even more ones. So you get to some very obscure things like minimal enclosing torus for a point set. This is something I have never actually used, but it can be formulated as such. And there are other stranger variations of this. So suffice to say, linear programming is pretty damn useful. And you can throw it at a lot of different problems in computational geometry. In fact, most low-dimensional polytope queries will turn into some variation of linear programming or another at the end of the day. Right? So all of these things like ray triangle intersection, for example, can be thought of as a special type of linear programming. Right? I mean, usually expanded out for the special case of a triangle and a ray, right? But still the same basic problem. So, okay, so I have about 7 minutes left, which is kind of awkward because not enough time to really get into anything terribly deep here. But I think I'll talk a little bit about distance queries right now. I don't know if I'll finish it or not, but I'm just going to give it a shot. So distance queries are kind of neat, and it's sort of an example of something that goes slightly beyond the vanilla sort of linear programming, right? We have to modify this a little bit into a form which is called quadratic programming, but it doesn't change any of the time complexities involved. It ends up being the same basic algorithms in all cases, right? And later on, we'll see how you can kind of generalize all of these things into a sort of combinatorial or algebraic framework that lets you, sort of crunch through these problems pretty efficiently. Right. So let me this. Like that. Here we go. All right, so I don't know if I'm going to get through this or not. We'll just make an effort. Okay. So distance queries, right? We're going to start with actually a simpler problem. We probably won't get to the convex version of this, right? But let's suppose we just have two affine subspaces represented in a primal form so that they're basically the join of some point sets. We would like to be able to calculate the distance between them. So for example, you have a point, you want to calculate the distance to the plane. You have two lines in 3D, you want to calculate the closest pair of points and the distance between them. These are things which show up all over the place in physics calculations for like systems of particles or other types of physical settings, right? They also show up like a lot in like a lot of like mundane things. So like even in like user applications, you maybe want to figure out like if you click on some button or whatever, how close are you to the boundary of some edge or some shape or whatever. So it's like pretty common operations. So here's the setting, right? So the distance, of 2 points, right, is basically just like the sum of their, vector distances, right? So this is basically, if we write this out, in matrix notation, it'll be x minus y, quantity transpose times x minus y, right? So that's the squared distance. So now let's suppose we have two sets, two flats. So two flats, we'll call them S, which is going to be the affine Hall of, let's say, some point set Pi. Can everyone read with this thing? Maybe I should switch to a different color. We have another set T, which is going to be the affine hull some set Qi. Right? Which means that if we take, the point P0 and leave it fixed, that this is going to be equal to the set of all points P0 plus A1, P1 minus P0, etc., plus AN, Pn minus P0, where these AIs are greater than or equal to, or no, I don't have any constraints on them. This is just affine space. That's right. This would be the set Q0 plus, let's call these B1, Q1 minus Q0, etc., plus B, let's call it M, Q sub M minus Q0. So these are just two flats, right? We can imagine that they're like lines or whatever, just in some d-dimensional affine coordinate system. Right? So the problem here that we want to solve is we want to compute the min x, or we're going to parameterize it in terms of the a's and b's, right? So we want to compute the min a in Rn, b in Rm of, let's define a couple of matrices to simplify this a bit. So we're going to define this whole thing to be the matrix P0 plus P transpose A, where P is going to be a matrix whose columns are the points, right? And this will just be Q0 plus Q transpose B, right? So this will be our point X. This will be our point Y. So this will be the min of P0 plus P transpose A minus Q0 minus Q transpose B squared. All right, so that's what we would like to minimize. So we're going to basically solve for the A and B vectors such that this will basically be as small as possible. I only have 3 minutes left, so I don't know that I'm going to actually get to much here. But OK, so the way we solve this turns out to be not so difficult, right? What we'll do is just square this thing, right? So if we do that, we're going to end up with, what does it look like? Right. We're going to have P0. I'm going to need more space. So I'll have to erase this, unfortunately. So if we, So if we square that whole mess here, right, we're going to get P0 minus Q0 squared plus 2 times P0 transpose PA minus it's actually, it should be P transpose A, right, minus Q0 transpose Q transpose B minus Q0 transpose P transpose A plus P0 transpose Q transpose B, then plus, we're going to use some matrix notation here. Right, this is A transpose B transpose. So it's basically a row vector, right, of the A's and B's times this matrix P transpose. Let's see here. This should be Q transpose. This will be P transpose Q transpose times A B. So just stacking them in there. So that's the sort of expansion of that form over there, right? It's a little bit larger. And what we want to do is minimize this again as a function of a and b. So if we do this, we can just take a derivative, right, as a function of a and b, and then set it equal to 0 for all the components, because this is just a positive semi-definite matrix here, right, which is the only quadratic term in this whole thing. So it's going to be convex, and it has a unique minimum, which is satisfied when the gradient of this thing is identically equal to 0. So if we do that, we're going to have a factor of 2 that comes down here, which will cancel out the other 2 there. This term is independent of a and b, so we can toss it out. So the final system, right, which is equivalent to minimizing this, actually turns out to be something quite pedestrian at the end of the day, which is that we just want to solve a single linear system, P transpose, PQ transpose, QP transpose, QQ transpose, AB equals to this right-hand side vector of P, what is this? I think it's P times P naught minus Q naught times Q of Q naught minus P naught. Right? So if you solve this single linear system, then you can compute the distance between a pair of affine spaces. And then the linear programming variation of this boils down to just adding additional constraints on A and B. Though there are other ways to set this up, and we'll look at them probably tomorrow because I'm already 2 minutes over. So I think this is a good place to stop for now.